Right now, 15.4 billion miles from where you are sitting, a spacecraft with less computing power than a modern greeting card is transmitting data through a backup transmitter that last powered on in 1981. It is the farthest human-made object in existence, and the boundary it was sent to cross, the edge of our solar system, turned out to be something nobody predicted. We are going to trace what Voyager actually found out there, from a secret love story encoded in brainwaves to a wall of pressure in interstellar space that science cannot explain. If this investigation grips you the way it should, hit subscribe now, because what comes next will change how you picture our place in the galaxy. Let's go. On August 25th, 2012, NASA held a press conference that made every major headline on the planet. Voyager 1, a spacecraft smaller than a compact car, had officially become the first human-made object to enter interstellar space. 40 years of flight, over 11 billion miles from home at the time. A boundary crossed that no machine, no satellite, no probe had ever reached. The announcement carried the weight of a species-defining moment, and for a few days, the world treated it exactly that way. Then the argument started. Within weeks of that press conference, a quieter narrative began circulating through the heliophysics community. Several prominent researchers pushed back on the claim. The data, they said, was ambiguous. One critical measurement had refused to cooperate with the theoretical predictions. Some argued the spacecraft was still inside the heliosphere, the protective bubble blown outward by charged particles streaming from our star. Others believed Voyager had entered a region nobody had ever described before, something between inside and outside. The debate dragged on for more than a year before NASA issued its formal confirmation in September 2013. Even that did not silence the dissenters. Leonard Fisk, a respected heliophysicist who had spent decades studying our star's magnetic influence, maintained as late as 2022 that the probe had never truly exited the heliosphere. His reasoning was specific, grounded in magnetic field data that we will get to shortly. He was not alone. A measurable fraction of the scientific community viewed the celebration as premature. Some published papers arguing the craft had entered a novel region that merely mimicked interstellar conditions. Others questioned whether the instrumentation, designed in the early 1970s, could reliably distinguish between a true crossing and a fluctuation. So consider this: the single greatest milestone in the history of unmanned spaceflight is contested by the very scientists whose work made it possible. The public was told the craft left the solar system. Researchers argued about what leaving even means. And buried inside that disagreement is a question that, nearly half a century after launch, remains genuinely unanswered. Where does the solar system actually end? That question sounds simple. It carries the kind of clean, definitive shape that suggests a clean, definitive answer, a boundary you can point to, a line on a map. Except every piece of data this spacecraft has returned over 48 years has made the answer harder, stranger, and more unsettled than it was before we had any data at all. The definition keeps shifting, the boundary keeps moving, the evidence keeps contradicting itself. We are going to follow the evidence. From a summer intern's hand-drawn plot in 1965 to a corrupted computer chip 15 billion miles from Earth. From a $900 million mission that Congress killed to a backup transmitter that woke up after 43 years of silence. What Voyager found at the boundary of our solar system broke models, ended careers, vindicated outcasts, and left science with more open questions than when the journey began. The investigation starts with a grad student, a pencil, and a once-in-a-lifetime alignment of 4 giant planets that nobody had noticed. In the summer of 1965, a young graduate student named Gary Flandreau walked into a corner office at the Jet Propulsion Laboratory in Pasadena, California. He was a summer intern, given a relatively mundane assignment: calculate future trajectories for missions to the outer planets. Nobody expected what he would find. What he did next would make the most ambitious space mission in history possible, and it began with nothing more sophisticated than a pencil and a stack of reference tables. Flandreau sat down with charts, orbital data, and those reference tables. No computer simulations, no orbital modeling software. Such tools barely existed in 1965. He plotted the positions of Jupiter, Saturn, Uranus, and Neptune over the coming decades, tracing arcs by hand across sheets of graph paper. And hidden in those arcs, he found something remarkable. All 4 gas giants were aligning on the same side of our star in a configuration that would allow a single spacecraft to slingshot from one planet to the next, using each world's gravity as a free accelerator. The window for this grand alignment would open in the late 1970s. It would not come again for 176 years. Think about that time frame. The last time these 4 planets lined up this way, the American Revolution had not yet begun. Mozart was a child. The next time the window opens, the year will be roughly 2153. Every human being alive in 1965 had exactly one chance to exploit this trajectory. And that chance had an expiration date measured in a few short years. Flandreau's discovery lit a fire inside the Jet Propulsion Laboratory. Engineers began sketching spacecraft designs. Physicists ran the numbers on gravity assists, calculating how much fuel could be saved by bouncing from planet to planet instead of flying direct. Each planetary encounter would bend the spacecraft's trajectory and add velocity, a cosmic slingshot that turned an impossible journey into a feasible one. The concept was staggering. A single mission could visit all 4 outer planets in a little over a decade, covering distances that would take conventional propulsion a lifetime. 2 spacecraft eventually launched from Cape Canaveral, separated by 16 days. The second to leave, on September 5th, 1977, was designated Voyager 1, placed on a faster trajectory that would get it to Jupiter and Saturn ahead of its twin. Voyager 2 had actually launched first, on August 20th, but its slower path meant it would arrive later at every stop. The naming was a bureaucratic quirk that still confuses people decades later. Together, these twin probes carried instruments designed for planetary flybys, cameras for photographing cloud bands and moons, magnetometers, cosmic ray detectors, and a power source that would become the most critical constraint of the entire mission. They also carried something else. A golden record, mounted on each craft's exterior, containing sounds and images chosen to represent life on Earth. But we will come back to that record and the extraordinary human story embedded in it. For now, what matters is the trajectory. Gary Flandreau had found the window, 2 spacecraft launched through it, and a mission that would eventually push farther from Earth than anything humans had ever built began with a hand-drawn plot and a 176-year cosmic coincidence that a summer intern noticed when nobody else did. The problem was that Congress had tried to kill the whole thing before a single rocket cleared the launch tower. The mission Flandreau's discovery inspired was originally called the Grand Tour. It was exactly as ambitious as the name suggests. NASA envisioned sending multiple spacecraft past all 4 outer planets, collecting data at each stop, building a comprehensive portrait of the solar system's most distant worlds. The estimated price tag came in at $900 million. In the early 1970s, that figure landed on the desks of congressional budget committees like a grenade. Congress killed the Grand Tour. The politics were straightforward. $900 million was an enormous sum for an unmanned space mission at a time when the Apollo program had already consumed public appetite for expensive exploration. The Vietnam War was draining budgets. Lawmakers saw no urgency in visiting gas giants. The alignment that Flandreau discovered was an interesting curiosity, but it did not translate into the kind of national prestige that had driven the race to the moon. The outer planets were not going anywhere, or so the argument went. ignoring the fact that the alignment window absolutely was. So the engineers at the Jet Propulsion Laboratory did what engineers do when the funding disappears. They repackaged the mission. The Grand Tour became Mariner Jupiter Saturn, a stripped-down version with a budget of roughly $250 million, less than a third of the original cost. The official scope was limited to Jupiter and Saturn only. Uranus and Neptune were cut from the approved itinerary entirely. Here is the critical detail that changes everything about this investigation. The extensions to Uranus and Neptune were never part of the approved plan. They were added later, one at a time, authorized piecemeal only after each previous flyby produced results impressive enough to justify continued funding. Every single discovery that Voyager made beyond Saturn happened on borrowed time, with borrowed money, aboard spacecraft that were officially supposed to have completed their mission billions of miles earlier. The termination shock, the heliopause crossing, the stagnation region, the anomalous cosmic rays, the magnetic field mystery, pressure front 2, all of it, every revelation that turned our understanding of the solar system's edge upside down came from a mission that, on paper, should have ended at Saturn's orbit. That is confirmed, by the way. You can trace the budget authorizations through NASA's own records. The Uranus flyby was approved only after Saturn delivered breathtaking results. Neptune came next, approved only after Uranus exceeded expectations. Each extension was a gamble. Any Congress, any budget committee, any single appropriations vote could have ended the mission at the boundary of the approved itinerary. The scientists and engineers who pushed for each extension knew they were asking for something that could be denied at any time. Which brings up a question worth sitting with. If the Grand Tour had survived, if the full $900 million had been authorized, would Voyager have been designed differently? Would different instruments have been included? Would the power systems have been built to last longer? The spacecraft we have now, pushing through interstellar space on under 300 watts, were designed for a Jupiter and Saturn mission. Everything beyond that is improvised. Every instrument still running was meant to shut down decades ago. Science believed the Grand Tour was the path. What actually happened was something messier, cheaper, more politically fragile, and ultimately more successful than any flagship mission could have been. A spacecraft designed for the inner edge of the outer solar system ended up at the outer edge of everything. But getting there required a decision at Saturn that would haunt the mission for decades. In 1980, Voyager 1 arrived at the ringed planet, and NASA confronted an irreversible fork in the road. Saturn's largest moon, Titan, was a high-priority scientific target. It possessed a thick, nitrogen-rich atmosphere, the only moon in the entire solar system known to have one. The prospect of studying that atmosphere up close was extraordinary. Flying close enough to do it in detail required a specific trajectory, calculated with precision down to fractions of a degree, and that trajectory carried a permanent consequence. The gravity assist needed to swing close to Titan would fling the craft upward, out of the plane where all the planets orbit. Once committed to that path, there was no correcting back. Pluto, which some mission planners had hoped to visit, became permanently unreachable. Every planet became permanently unreachable. The Titan flyby would transform Voyager 1 from a planetary explorer into something else entirely, a projectile aimed at the edge of the solar system, with no stops between Saturn and whatever lay beyond the heliosphere. NASA chose Titan. From that moment, the craft's destiny was sealed. It would fly outward, alone, for as long as its instruments and power held out. The only things it would encounter were the boundaries of our star's influence, whatever existed beyond them, and the empty stretches in between. Everything about the craft's future became a question of endurance rather than destination. Before launch, though, the team had prepared something for the long silence ahead. Carl Sagan, the astronomer who had already become the public face of planetary science, led an effort to create a message from Earth that would travel aboard both spacecraft. The result was the golden record, a gold-plated copper disc containing 116 images, greetings in 55 languages, 90 minutes of music from cultures around the world, and an assortment of natural sounds from wind and surf to birdsong and laughter. The record cost $18,000 to produce. The Beatles had approved Here Comes Our Star for inclusion, one of the most recognizable songs on the planet. Then the record label that held the rights demanded $100,000 in licensing fees. The entire record's budget was less than a fifth of that demand. The song was cut. In its place, the team selected other pieces of music that could be secured for free or at minimal cost. What did make it onto the disc is, in some ways, stranger and more human than any popular song. Anne Druyan, a creative director working with Sagan on the record project, had her brainwaves recorded by an electroencephalograph and compressed into a minute of audio for the disc. She and Sagan had fallen in love during a late-night phone call about the project, days before the recording session. They had told no one. As the electrodes traced her neural patterns, Druyan later said she was thinking about the history of Earth, the nature of love, and what it felt like to be falling for a specific person in a specific moment. Those brainwaves are now aboard both Voyager spacecraft, over 15 billion miles from the lab where they were recorded. Carl Sagan later divorced his wife, who had also worked on the Voyager project. It was messy, painful, and entirely human. The golden record carries the fingerprints of that complicated moment, along with everything else. With Titan studied and Pluto sacrificed, the craft turned its instruments outward. Ahead lay the space between planets, then the space between stars. The question shifted from what the probe would fly past to what invisible boundary it might someday cross. Scientists had a clear picture of what that boundary should look like. It had been in the textbooks for decades, and virtually everyone agreed on the details. For more than 55 years, the model of our star's influence on surrounding space was clean, intuitive, and almost universally accepted. Our star blows a constant stream of charged particles in every direction, a flow of protons and electrons racing outward at hundreds of miles per second. Physicists call this the solar wind. That wind inflates an enormous bubble, hundreds of times wider than the distance from our star to Earth, pushing outward against the thin gas and dust that fills the space between stars. This bubble has a name: the heliosphere. At some distance from our star, the solar wind slows down. It decelerates from supersonic speeds to subsonic speeds at a boundary called the termination shock. Think of a bullet slowing to below the speed of sound. The physics are similar. Beyond the termination shock, the wind continues outward, but more slowly, compressed and heated as it pushes against the interstellar medium. This region between the termination shock and the outer edge of the bubble is called the heliosheath. And at the outermost edge of the heliosheath sits the heliopause, the wall, the final boundary where our star's influence gives way to the galactic environment. Cross the heliopause, and you are, by the most commonly used definition, outside the solar system and inside interstellar space. Every textbook showed this bubble with a distinctive shape. Because our star moves through the galaxy at a considerable speed, the heliosphere was drawn with a blunt nose facing forward and a long, tapering tail streaming behind, like a comet. The analogy was simple, the physics seemed straightforward, and nobody had data to contradict it. For over half a century, the comet-tail heliosphere became one of those background assumptions that an entire field built upon without questioning. It appeared in textbooks, on diagrams, in grant proposals, and in the mental models of every heliophysicist on the planet. Stamatios Krimigis, a researcher who would later play a key role in interpreting Voyager data, put it plainly. "You don't accept that kind of change easily," he said. The whole scientific community had assumed for over 55 years the heliosphere had a comet tail. The model also predicted specific, measurable events at each boundary. At the termination shock, the solar wind would decelerate abruptly. A population of particles called anomalous cosmic rays would be accelerated to their observed energies right at the shock front, bouncing back and forth across the boundary like a ball gaining speed between two converging walls. At the heliopause, the magnetic field would rotate sharply, pivoting from our star's field direction to the galactic field direction. This rotation was considered the single clearest signature that a spacecraft had crossed from inside to outside. Scientists expected Voyager to confirm each prediction in sequence. Termination shock. Solar wind decelerates. Confirmed. Heliopause. Magnetic field rotates. Confirmed. Interstellar space. Galactic cosmic rays dominate. Confirmed. A textbook checklist of boundary crossings, validated one by one. The models were built by brilliant people working from solid physics. Decades of theoretical work had refined the predictions. The heliosphere was supposed to be a solved problem, with Voyager serving as the final confirmation rather than the opening chapter of a new mystery. On February 14, 1990, the craft paused its outward flight long enough to turn its camera backward, and what it captured in that single image would reshape the emotional context of every boundary crossing still to come. The image arrived on Earth as raw data, transmitted at 160 bits per second from a distance of approximately 3.7 billion miles. When processed, it showed our planet as a pale point of light, occupying 0.12 pixels of the camera's frame. Scattered beams of reflected radiation from the camera's optics crossed the image, and Earth sat inside one of those beams, barely distinguishable from a defect in the lens. Carl Sagan would later use this photograph to write one of the most quoted passages in the history of science communication. Every war, every love story, every civilization that had ever existed, captured in a fraction of a pixel from the vantage point of 40 astronomical units. But the scientific implications were different from the poetic ones. At 40 astronomical units, Voyager 1 had covered less than half the distance to the termination shock. The heliosphere's inner boundary was still decades of flight time away. The edge of the solar system remained an abstraction, a theoretical line on a chart somewhere in the future. After capturing the pale blue dot, mission controllers made a practical decision. The cameras were shut off permanently. Voyager 1 would never photograph anything again. The power those cameras consumed was needed elsewhere, for the instruments that would matter when the spacecraft eventually reached the boundaries that its cameras could never have seen anyway. You cannot photograph the termination shock. You cannot take a picture of the heliopause. These boundaries are invisible, defined by particle counts and magnetic field measurements, not by visible light. What followed was 14 years of near silence. The craft continued outward at roughly 38,000 miles per hour. Its instruments ran continuously, measuring the solar wind, counting cosmic rays, mapping magnetic field direction and strength. The data trickled homeward at 160 bits per second through a signal so faint that its power, arriving at the massive receiving dishes of the Deep Space Network, registered at 10 to the power of minus 16 watts. For perspective, a typical household light bulb uses 60 watts. The signal from the most distant human-made object in existence delivers a fraction of a watt so small that you need 16 zeros after the decimal point to express it. The craft's onboard computer held 3 million times less memory than a modern cell phone. Its entire data processing architecture was designed in the early 1970s, before the first Apple computer existed, before the internet, before anyone had conceived of a smartphone. Every measurement, every cosmic ray count, every magnetic field reading was captured, packaged, and transmitted by hardware that predated the personal computer revolution by nearly a decade. For 14 years, the data showed a gradually declining solar wind and a slowly increasing cosmic ray count. The trends matched the models. The approach to the termination shock looked exactly as predicted, a steady, orderly march toward the first boundary. The scientific community expected a clean, confirmatory arrival, December 2004 shattered that expectation. The data that arrived in those transmissions contained signatures that did not match any model on any whiteboard at any institution on Earth. The first boundary had been reached, and the shock, when they analyzed it, was not the confirmation science had waited for. It was the beginning of every assumption falling apart. On December 16, 2004, Voyager 1's instruments registered an abrupt change. The solar wind velocity dropped. Particle energies shifted. The signatures were consistent with a single interpretation. The spacecraft had crossed the termination shock at 94 astronomical units from our star. After 27 years of flight and decades of theoretical prediction, the craft had reached the first boundary of the heliosphere's edge. The scientific community held its breath. Then, the wait began for the second data point. Voyager 2, traveling a different path on the opposite side of the heliosphere, was still approaching. It reached the termination shock on August 30th, 2007, 3 years after its twin. The distance from our star at that crossing was 84 astronomical units. 84, compared to 94, a gap of 10 astronomical units. In miles, that difference is approximately 930 million, more than the distance from our star to Saturn. Let that register for a moment. The two spacecraft had crossed the same boundary, the same physical phenomenon, at distances separated by roughly 1 billion miles. The heliosphere, which every model had treated as roughly symmetric, was profoundly lopsided. Something external was pressing harder on one side than the other. The interstellar medium, the thin gas and magnetic field that fills the space between stars, was apparently denser or more forceful on the flank where Voyager 2 flew. The bubble protecting our solar system was being squished, deformed, pushed inward on one side while extending farther outward on the other. A single measurement can be an anomaly, instrument error, a transient fluctuation, a local disturbance that happened to coincide with the crossing. Two measurements from different spacecraft in different locations, years apart, carrying the same implication, constitute evidence that demands explanation. The symmetric heliosphere, a cornerstone of 5.5 decades of theoretical work, was finished as a viable model. The confirmation scientists had expected instead delivered a contradiction. The boundary was real. Its location was profoundly non-uniform. The shield around our solar system was warped, distorted, shaped by forces that the models had failed to account for. That alone would have been enough to rewrite the textbooks. But the termination shock held a second surprise, and this one struck at the heart of particle physics models that had been considered settled for years. The anomalous cosmic rays were supposed to receive their energy at this boundary. The termination shock was, according to prevailing theory, the accelerator. Particles from the interstellar medium that had been ionized and captured by the solar wind would bounce back and forth across the shock front, gaining energy with each pass, until they reached the enormous velocities observed by instruments closer to Earth. The mechanism was well understood in theory, elegant even. The termination shock was the engine that powered one of the most energetic particle populations in the heliosphere. Voyager 1 crossed that engine. The anomalous cosmic ray count did not peak. It did not level off. It continued to climb. Beyond the shock, deeper into the heliosheath, the particles kept gaining energy from an unknown source. The boundary that was supposed to be the explanation turned out to need an explanation of its own. Whatever was accelerating those particles existed farther out or operated through physics that no existing framework described. And the question of where the solar system ends had just become significantly more complicated, because if the first boundary was already this wrong, what would the second one reveal? When Voyager 2's instruments captured their version of the termination shock crossing, the data included something that made researchers at the Applied Physics Laboratory sit up straight. Pickup ions, atoms from the interstellar medium that had been stripped of their electrons and swept up by the solar wind, were carrying vastly more energy than any model had predicted. The theoretical frameworks had accounted for these particles, but had drastically underestimated their energy contribution to the overall system. Ralph Brandt, reviewing the data from the Voyager 2 crossing, offered a reaction that would become famous within the heliophysics community. Looking at the numbers from the termination shock instruments, his response was a single word: what the fuck? The pickup ions mattered because they represented a population of particles that the models had essentially treated as minor players. Background noise. Passengers on the solar wind, present but dynamically unimportant. Instead, they turned out to be carrying a significant fraction of the total energy budget at the termination shock. The minor players were, in reality, heavyweights that had been invisible to theory for decades, dominating the energy dynamics of the very boundary where they were supposed to be irrelevant. Combined with the anomalous cosmic ray puzzle from Voyager 1's earlier crossing, the picture of the termination shock that emerged was fundamentally different from the one in the textbooks. The boundary existed. Its basic nature, a transition from supersonic to subsonic solar wind, was confirmed. But nearly everything else about it, its distance from our star, its symmetry around the heliosphere, its role as a particle accelerator, and the energy balance of the particles within it, deviated from predictions in ways that demanded new physics, or at minimum new models. The investigation was approaching its most important boundary, the heliopause, the outer wall of the heliosphere, the line that separates our star's domain from interstellar space. Every prediction that had failed at the termination shock raised the stakes for what would happen at the next crossing. If the models were this wrong about the first boundary, the boundary that was supposed to be simpler and better understood, could they be trusted about the second? There was another problem, a practical one that had nothing to do with theoretical physics. An engineering failure from decades earlier was about to collide with the most important scientific measurement of the entire mission. To detect the heliopause, to actually prove that a spacecraft had crossed from inside the heliosphere to outside, researchers needed one type of measurement above all others: the density, temperature, and behavior of the plasma surrounding the spacecraft. Was the craft immersed in hot, sparse solar wind plasma, or had it transitioned into the cooler, denser plasma of the interstellar medium? The instrument designed to answer that question was the plasma science experiment. It measured charged particles directly, providing the clearest possible window into the spacecraft's plasma environment. Voyager 1's plasma science experiment had failed at Saturn. In 1980, the one instrument most critical for confirming the crossing had been dead for over 3 decades by the time the spacecraft approached the heliopause. The detector that would have provided unambiguous, direct measurements of the plasma transition had gone dark at the worst possible moment in the worst possible location. It had been dead for longer than many of the scientists now analyzing the data had been alive. Voyager 2 still had a working plasma detector, but Voyager 2 was years behind, still working its way through the heliosheath. The spacecraft closest to the edge, the one that would get there first and make history first, was essentially flying blind to the single measurement that mattered most. Scientists would have to find another way to determine whether the craft had crossed the boundary. They would have to improvise. To detect the heliopause without a plasma detector, the team turned to indirect methods. The plasma wave instrument, originally designed to study oscillations in magnetized plasma near the giant planets, could infer the density of the surrounding medium by measuring the frequency of naturally occurring plasma waves. Higher frequencies meant denser plasma. The cosmic ray instruments could track shifts in particle populations. The magnetometer could map changes in field strength and direction. Together, these instruments could build a circumstantial case for or against a crossing. But circumstantial evidence invites disagreement, and disagreement is exactly what happened. Between 113 and 122 astronomical units from our star, something was waiting that would make the improvisation even harder. Between 113 and 122 astronomical units from our star, Voyager 1 entered a region that had no name because nobody knew it was there. The stagnation region, as scientists would eventually call it, had never appeared in any model. No theoretical framework predicted its existence, its location, or its behavior. The solar wind, that constant outward stream of charged particles, had been slowing for years as the spacecraft pushed deeper into the heliosheath. The gradual deceleration was expected. What happened at 113 astronomical units was something else entirely. The radial velocity of the solar wind dropped to zero. The stream that had been blowing outward from our star for billions of miles simply ceased to move. Then something stranger happened. The wind went further than stopping. It reversed direction. Instruments detected lateral and backward flows, as though the solar wind was folding back on itself, tumbling in directions that had no relationship to the expected outward pattern. The heliosphere appeared to be collapsing inward in this region, the wind piling up against some external pressure and rebounding in chaotic, directionless motion. For 9 astronomical units, approximately 840 million miles, Voyager 1 flew through this disordered zone. The solar wind was present, but purposeless, its energy dissipating into turbulent eddies rather than flowing in any coherent direction. The magnetic field fluctuated unpredictably. Particle counts oscillated without pattern. Everything about this region suggested a system under extreme stress, a bubble being squeezed from outside with enough force to stall and reverse the wind that had been blowing steadily outward for billions of miles in every other region the craft had traversed. The stagnation region was a clue. A large, loud, 900 million mile wide clue that something complicated was happening at the boundary. The heliopause, wherever it was clearly not going to be a clean line. If the approach was this chaotic, the crossing itself would carry complications that no model had anticipated. Consider what the investigation had established by this point. The termination shock was 10 astronomical units closer on one side of the heliosphere than the other. Anomalous cosmic rays were not being accelerated where theory said they should be. Pickup ions carried energy that models had ignored for decades. The one instrument needed to confirm the heliopause crossing was dead, and now a region of reversed chaotic solar wind filled the space before the boundary, a buffer zone 900 million miles wide, whose existence was a complete surprise. Every model had predicted a sequence of clean transitions. Wind slows, wind stops, cross the boundary, enter interstellar space. Instead, the approach looked like a system failing in stages, with each stage more disordered than the last. The textbook diagram, with its neat, concentric zones and crisp boundary lines, bore almost no resemblance to what the instruments were actually recording. And somewhere ahead, past the stagnation region, past the turbulence and the reversed flows and the confused magnetic fields, the heliopause waited. The boundary where the solar wind ends and the interstellar medium begins. The moment the entire mission had been building toward for 35 years. Voyager 1 was approaching it with a dead plasma detector, a violated set of model predictions, a stagnation region at its back that should never have existed, and a team of scientists who would have to argue about what the data meant because they could not measure the one thing that would have settled the question directly. The crossing, when it came, would deliver the biggest surprise yet, and it would ignite a debate that lasted more than a year. On August 25th, 2012, at 121.6 astronomical units from our star, Voyager 1's instruments registered a dramatic shift. Galactic cosmic rays, high-energy particles, originating from supernova remnants, neutron stars, and other violent events scattered across the Milky Way, surged upward. The count jumped by a factor of 3. Simultaneously, the lower energy particles associated with our star's influence plummeted. The two measurements moved in opposite directions with a sharpness that left little room for interpretation. By every particle measure, the spacecraft had crossed the heliopause, But one critical measurement refused to cooperate: the magnetic field. Every model of the heliopause predicted that at the boundary, the direction of the magnetic field would rotate sharply. Inside the heliosphere, the field is shaped and oriented by our star. Outside, the galactic magnetic field dominates, and its orientation is different. The transition from one field to the other was supposed to produce a measurable, unambiguous rotation in the magnetometer data. This was the signature, the single most anticipated confirmation that a spacecraft had left our star's domain and entered interstellar space. The rotation never came. The field strength changed. That much was clear. But its direction remained essentially the same on both sides of the boundary. The compass needle, metaphorically speaking, should have swung. It held steady. The implication was staggering. Either the models were wrong about the magnetic field at the heliopause, or the spacecraft had not actually crossed the heliopause, or the boundary itself was something different from what anyone had imagined. This missing signature threw the entire crossing into doubt. Within the heliophysics community, arguments erupted immediately. Researchers who had spent careers building models of the heliopause confronted data that contradicted the one prediction they considered most reliable. Some accepted the particle evidence and treated the magnetic anomaly as a mystery to be solved. Others argued that without the magnetic field rotation, the crossing could not be considered confirmed. The debate lasted more than a year. Papers were published, arguing both sides. Conference panels devolved into heated exchanges. The public had been told the probe left the solar system. Behind the scenes, the scientists who made that announcement were fighting about whether it was true. And here is the detail that makes this particular failure so significant. When Voyager 2 crossed the heliopause 6 years later, at a different distance, on a different trajectory, on the opposite side of the heliosphere, the magnetic field direction once again failed to change. The same anomaly, the same missing rotation. Two independent crossings, separated by 6 years and billions of miles, producing the same impossible result. This was confirmed data, replicated by both spacecraft. The magnetic field at the heliopause does something that no model in the history of heliophysics had predicted. The question of whether Voyager 1 had truly left was about to find its most vocal skeptic, and his argument would hold up for a decade. Leonard Fisk was not a contrarian or a fringe figure. He was one of the most respected heliophysicists in the world, with decades of published work on our star's magnetic influence and the dynamics of the solar wind. When he looked at the Voyager 1 data from August 2012, he reached a conclusion that put him at odds with NASA's official announcement. The spacecraft, he argued, had not left the heliosphere. His reasoning centered on the magnetic field. If Voyager 1 had truly entered interstellar space, the surrounding magnetic field should reflect the galactic environment. The direction should have changed. It did not. Fisk proposed an alternative explanation. The craft had entered a previously unknown region of the heliosphere itself, a zone where particle populations mimicked interstellar conditions while the magnetic environment remained solar in origin. A kind of antechamber, still inside the bubble, where the usual markers of inside and outside became unreliable. The proposal was not wild speculation, it was grounded in the actual data. The unchanged magnetic field was a fact. The particle transition was also a fact. Fisk argued that the particle data alone was insufficient to confirm a crossing when the magnetic data contradicted it. He had a point. Without direct plasma measurements, which the dead plasma science experiment could have provided, the evidence was inherently incomplete. The strongest confirmation would have come from an instrument that had been silent for over 30 years. Other scientists lined up behind him. The year-long debate that preceded NASA's formal announcement in September 2013 was not a formality. It was a genuine scientific argument in which credible researchers, using the same data, reached opposite conclusions. Fisk maintained his position for years afterward, publishing papers as late as 2022 that questioned whether the craft had truly exited our star's domain. His argument highlights something important about how science actually works at the frontier. When a spacecraft crosses a boundary that has never been crossed before, there is no independent verification. Nobody can fly out and check. The only data comes from the instruments on the craft itself, and when those instruments disagree with each other, the interpretation depends on which instruments you trust more and which theoretical framework you bring to the table. The heliopause crossing was supposed to be clean. Instead, it became a case study in scientific ambiguity. The particles said one thing, the magnetic field said another. The plasma detector, which could have broken the tie, was dead. And the boundary itself turned out to be far stranger than anything the models had prepared researchers to expect. The deadlock might have continued indefinitely. It might still be unresolved, debated in journals and at conferences with no clear resolution in sight. Except that one physicist had made a prediction 20 years before the crossing, been laughed at for it, and left behind an instrument that would ultimately tip the scales. In 1992, a physicist named Don Gurnett detected faint radio wave emissions emanating from the outer reaches of the heliosphere. The signals were weak, intermittent, and easy to dismiss. Gurnett did not dismiss them. He analyzed their frequencies and used the data to calculate the distance to the heliopause, somewhere between 116 and 177 astronomical units from our star. The prediction was met with skepticism. The data was thin. The range was wide. Other researchers considered it speculative, the kind of estimate that would be remembered only if it happened to be correct and forgotten instantly if it was wrong. Gurnett published his findings and moved on to other work. The prediction sat in the literature for 2 decades, largely ignored. Then Voyager 1 crossed the heliopause at 121.6 astronomical units, squarely within Gurnett's predicted range. 20 years of being dismissed, and the data had proven him right. But Gurnett's contribution went beyond the prediction. His plasma wave instrument, still functioning on Voyager 1, became the key to resolving the debate that Fisk and others had ignited. The plasma science experiment was dead. Yes, direct plasma measurements were impossible, but the plasma wave instrument could do something indirect and enormously valuable. It could detect oscillations in the surrounding medium and, from the frequency of those oscillations, infer the density of the plasma around the spacecraft. In the months after the crossing, the instrument detected a sharp increase in plasma oscillation frequency. The implied density jump was approximately 40-fold, from the hot, sparse plasma of the solar wind to a cooler, significantly denser medium, consistent with the interstellar environment. 40 times denser. The transition was abrupt and unambiguous. While the magnetometer showed no change in field direction, the plasma wave instrument showed a change in density so dramatic that it was difficult to explain as anything other than a boundary crossing. This was the evidence that tipped the scales. NASA officially announced the heliopause crossing in September 2013, relying heavily on Gurnett's plasma wave data. The particle evidence was strong. The magnetic evidence was contradictory. The plasma wave evidence broke the tie. Don Gurnett died on January 13, 2022. He did not live to see Pressure Front 2, the 2024 engineering crisis, or the transmitter failure that nearly silenced the mission. But his instrument remains active, and his prediction, mocked for 2 decades, stands as one of the most precisely vindicated forecasts in the history of space physics. The investigation had its first confirmed crossing. The debate was settled, at least officially. 6 years later, the second spacecraft would reach the same boundary, carrying the one instrument its twin was missing. The expectation was straightforward. Voyager 2's working plasma detector would provide the direct confirmation that Voyager 1 could never deliver. That expectation, like so many others in this story, was about to get complicated. On November 5, 2018, Voyager 2 crossed the heliopause at approximately 119 astronomical units from our star, 2.6 astronomical units closer than where its twin had crossed 6 years earlier. The difference in distance was notable, but not necessarily surprising given the heliosphere's established asymmetry. What mattered about this crossing was the instrument package. Voyager 2's plasma science experiment still worked. For the first time, a spacecraft could directly measure the plasma transition at the heliopause rather than inferring it from indirect instruments. The data was sharp. A sudden, dramatic jump in plasma density confirmed the boundary. The craft had crossed from the solar wind environment into the denser interstellar plasma, and the plasma detector recorded the transition in real time. The crossing was confirmed. Directly, unambiguously, with the instrument designed for exactly this measurement. But several details refused to align with the first crossing. The two spacecraft crossed at different distances, on different sides of the heliosphere, years apart. Each found a sharp plasma transition. Each measured changes in cosmic ray populations. And at both crossings, the magnetic field direction failed to change. Twice now. Two independent spacecraft, two independent magnetometers, two independent crossings separated by billions of miles. The same result. The magnetic field at the heliopause does something fundamentally different from what 5 decades of theoretical work predicted. This was no longer an anomaly of Voyager 1. This was a confirmed feature of the boundary itself. The two crossings, taken together, painted a picture of a heliopause far more complex than any pre-mission model had anticipated. Some properties changed sharply: plasma density, cosmic ray counts, the energy spectrum of particles from our star. Other properties remained stubbornly continuous. The magnetic field direction, which should have been the clearest marker of all, transitioned smoothly, if it transitioned at all. Nobody had a complete explanation. Theories circulated. Perhaps the magnetic fields of the heliosphere and the interstellar medium were, by cosmic coincidence, aligned at the locations where both spacecraft crossed. Perhaps the boundary layer was thick enough that the magnetic transition occurred gradually over a vast distance rather than sharply at a single surface. Perhaps the interaction between the two fields produced a complex, layered structure that neither theory nor previous observation had anticipated. Each theory had strengths, each had problems. None had consensus. The investigation had reached the point where the confirmed data was more confusing than the absence of data had been. Both crossings were real, both were documented with instruments functioning at the boundary, and both produced a result that, by every theoretical framework in existence, should have been impossible. At that boundary, the instruments also recorded something that defied physical intuition entirely. At the heliopause, both Voyager spacecraft measured the temperature of the surrounding plasma. The readings came back between 30,000 and 50,000 Kelvin. In Fahrenheit, that translates to 54,000 to 90,000 degrees. For context, the visible surface of our star is approximately 5,500 Kelvin. The edge of the solar system, at the point where our star's influence finally gives way to the interstellar medium, is between 5 and 9 times hotter than the stellar surface itself. The coldest, most remote frontier imaginable turned out to be a furnace. The reason the spacecraft did not melt is density. Temperature, in physics, measures the average kinetic energy of individual particles. At the heliopause, each particle is screaming along at velocities that correspond to tens of thousands of degrees, but there are almost none of them. The plasma is so sparse that the total energy it carries is negligible. Think of it this way: a single ember from a campfire might be at 2,000 degrees Fahrenheit. If that single ember lands on your hand, you brush it off. The temperature is real, but the density is so low that virtually no energy transfers to your skin. At the heliopause, the principle is the same, scaled up to cosmic dimensions. Individual particles carry enormous energy. There are so few of them per cubic meter that the craft drifts through unscathed. But the temperature itself demands explanation. How does a region at the absolute farthest reach of our star's influence, where the solar wind has been decelerating and cooling for billions of miles, end up hotter than the stellar surface? The solar wind at Earth's orbit is roughly 100,000 to 300,000 degrees Fahrenheit. By the outer heliosphere, it has cooled considerably. At the termination shock, compression reheats it somewhat, but the temperatures measured at the heliopause exceeded anything the compression models predicted. The leading explanation involves the piling up effect. As the solar wind approaches the heliopause, it compresses against the interstellar medium. That compression converts kinetic energy into thermal energy, heating the plasma. Pickup ions, those interstellar atoms captured and accelerated by the solar wind, contribute additional energy that the older models had not accounted for. The same pickup ions that produced the what the fuck reaction at the termination shock may play a role in heating the heliopause region to its extreme temperatures. But no model fully reproduces the measured values. The confirmed temperature range at the boundary is a fact that theory is still working to explain. The edge of the heliosphere was supposed to be a quiet, cooling frontier where the last gasps of the solar wind faded into the interstellar darkness. Instead, it registered temperatures that would vaporize steel if the density were higher. The investigation had now established that the boundary was asymmetric, magnetically anomalous, debated by its own discoverers, and absurdly hot. The question of its shape, the large-scale geometry of the entire heliosphere, was about to collapse into chaos. For more than 55 years, every diagram of the heliosphere showed the same shape, a blunt nose pointing in the direction of our star's motion through the galaxy, and a long tail streaming behind. Like a comet, the image was in every textbook, every lecture slide, every public presentation about the boundary between our star's domain and interstellar space. The comet tail was intuitive. Our star moves through the galaxy. The solar wind gets compressed in front, stretched behind, windsock in a breeze. The physics seemed obvious. Then the Cassini spacecraft, before its deliberate destruction in Saturn's atmosphere in 2017, provided an unexpected piece of evidence. Its instruments had been mapping energetic neutral atoms, particles that form when charged solar wind particles exchange electrons with neutral interstellar atoms. Those measurements covered a broad swath of the sky and produced a map of the heliosphere's boundary as seen from inside. The shape that emerged was not a comet. It looked more like a beach ball, roughly spherical, no elongated tail. The data suggested that whatever was happening behind our star's direction of motion was not the long, tapering wake that every model predicted. Meanwhile, heliophysicist Merav Ofer had been running magnetohydrodynamic simulations of the heliosphere. Her models did not produce a comet either. They produced something far stranger, two lobes of solar material curling backward from our star, twisted by the stellar magnetic field into a shape that, from certain angles, resembled a croissant. Two fat jets, spiraling outward, with no straight tail at all. When she presented this at conferences, the response was hostile. Ofer described being bashed at every conference where she showed the croissant model. The comet tail shape was not merely a theoretical prediction. It was a consensus so deeply embedded that challenging it meant challenging the professional legacy of an entire generation of researchers. Career reputations, publication records, and grant histories were built on the comet tail heliosphere. Other researchers proposed a jellyfish shape, with trailing tentacles of magnetic field and plasma streaming asymmetrically behind the heliosphere. Crimigas captured the emotional weight of the moment. You don't accept that kind of change easily. The whole scientific community had assumed for over 55 years the heliosphere had a comet tail. As of today, confirmed in the most recent literature, there is no consensus on the shape of the heliosphere. The comet is not dead, but it is no longer the default. The beach ball, the croissant, and the jellyfish are all active contenders. The shape of the bubble protecting every living thing in our solar system from galactic radiation remains genuinely unknown. Merv Ofer did not set out to start a fight. Her magnetohydrodynamic simulations, among the most sophisticated computational models of the heliosphere in existence, simply did not produce the expected result. Where every previous model generated a comet tail, hers generated two jets of magnetized solar material curling backward from our star, twisting around each other under the influence of the rotating stellar magnetic field. The physics driving the croissant shape was specific and reproducible. Our star's magnetic field flips polarity roughly every 11 years during the solar cycle. That oscillating field imprints itself on the outflowing solar wind, creating alternating sectors of positive and negative magnetic polarity. When this striped wind reaches the outer heliosphere and piles up against the interstellar medium, the alternating sectors interact, reconnect, and produce a bifurcated structure rather than a smooth tail. Two lobes, twisting, curling, like dough folding over itself. The results were reproducible. Other groups ran similar simulations and obtained similar structures. The underlying physics was sound. Ofer published paper after paper, each one refining the model, each one met with resistance at conferences, where the comet tail had been dogma for half a century. What made the resistance so intense was not the quality of her work, it was the implication. If the heliosphere is shaped like a croissant rather than a comet, then the theoretical framework underlying decades of research on how the heliosphere interacts with the interstellar medium needs revision. Cosmic ray propagation models change. Estimates of the heliosphere's shielding effectiveness change. The way we predict how the bubble will respond to changes in the interstellar environment changes. A different shape means a different interaction with the galaxy, which means different consequences for everything inside the bubble. The Voyager data supported the complexity. The asymmetric termination shock, with its 10 astronomical unit discrepancy between the two crossings, was more consistent with a complex, multi-lobed structure than with a smooth, symmetric comet. The chaotic stagnation region, where the solar wind reversed and lost coherence, was easier to explain in a geometry with complex internal dynamics than in a simple tail. The unchanged magnetic field direction at the heliopause made more sense in a structure where the boundary was thick and layered rather than thin and sharp. Ofer was not vindicated overnight. The debate remains active. But the comet tail is no longer the automatic assumption. That shift, which represents one of the most significant conceptual changes in heliophysics this century, happened largely because one researcher kept publishing results that the community did not want to see. While Ofer was fighting for a new shape, a telescope orbiting Earth captured something that did not fit any shape at all. In 2009, NASA launched the Interstellar Boundary Explorer, a small satellite designed to map the heliosphere's outer boundary from Earth orbit. It detected energetic neutral atoms, particles that form when fast-charged particles from the heliosphere's edge exchange electrons with slow neutral atoms in the interstellar medium. Those neutral atoms, no longer deflected by magnetic fields, fly in straight lines back toward Earth, carrying information about conditions at the boundary where they were created. The Interstellar Boundary Explorer mapped these atoms across the entire sky. What it found was a ribbon, a bright, narrow band of energetic, neutral atom emissions stretching across the celestial sphere. The ribbon was concentrated, coherent, and completely unexpected. No existing model of the heliosphere had predicted its existence. No simulation had produced it. No theory of the interaction between the solar wind and the interstellar medium had suggested that a focused ribbon of emissions should appear in the data. The Interstellar Boundary Explorer team used a phrase that would be quoted for years. The ribbon was not resembling any theory. In the 15+ years since its discovery, the ribbon has generated dozens of papers and multiple competing explanations. One leading hypothesis suggests that the ribbon marks a location where the interstellar magnetic field is perpendicular to the line of sight from Earth, creating conditions where secondary energetic neutral atoms are preferentially directed back toward the inner solar system. Another proposes instabilities at the heliopause that create localized enhancements in particle production. A third involves the draping of the interstellar magnetic field around the heliosphere, producing a focused emission region. None of these explanations has achieved consensus. The ribbon remains one of the most significant unexplained features in heliophysics, a structure that implies an interaction between the heliosphere and its surrounding environment that was invisible to theory until an instrument happened to look for it. The implications extend beyond academic interest. If the boundary of the heliosphere produces focused emissions that no model predicted, then our understanding of how the boundary works is incomplete in a fundamental way. The heliosphere is the radiation shield for the entire solar system. Understanding its boundary means understanding how well it protects us. The ribbon suggests that protection operates through mechanisms we have not yet identified, and the ribbon was not the last surprise from interstellar space. In 2020, the craft that had crossed the heliopause 8 years earlier detected something out there that nobody can explain. In 2020, Voyager 1 was sailing through what was supposed to be the relatively uniform interstellar medium, over 150 astronomical units from our star, well past the heliopause, well past the stagnation region and the termination shock and every known boundary of the heliosphere. The spacecraft was, according to every definition in use, in interstellar space. Its instruments detected a sudden change. Plasma density jumped by approximately 30%. The magnetic field strength increased by a comparable fraction. Both measurements rose together and stayed elevated for days, then weeks, then months, then years. As of the most recent data available, more than 5 years after the initial detection, the elevated values persist. Scientists designated the phenomenon Pressure Front 2. Consider the strangeness of this. Voyager 1 is moving through a region that was supposed to be a featureless void. The interstellar medium, in textbook descriptions, is the space between stars, thin, uniform, slowly varying over distances of light years. Finding a sharp, persistent structure at the scale of a single spacecraft's path was not anticipated. There should be nothing out there to create a 30% jump in density that sustains itself for half a decade. Nobody knows what Pressure Front 2 is. The theories range from a compression wave generated by a distant stellar event, perhaps a supernova shock front that has propagated through the interstellar medium over thousands of years, to a boundary of a previously unknown interstellar structure, like a wall of denser material that the heliosphere is approaching or already interacting with. Some researchers have suggested it could be related to the heliosphere's own wake, a disturbance created by our star's passage through the medium that Voyager is now encountering from the other side. Each theory has problems. A supernova shock should dissipate over the distances involved. A static wall of denser material should have been visible in other measurements. A heliospheric wake should have predictable characteristics that do not match the data perfectly. What Pressure Front 2 demonstrates, with confirmed data from instruments operating in real time 15 billion miles from Earth, is that interstellar space contains structures, organized, persistent, measurable structures that do not appear in any existing map because nobody has ever had an instrument out there to detect them before. We have exactly one data point on each structure from exactly one trajectory through the interstellar medium, observed by exactly one spacecraft. The investigation was piling up mysteries faster than it was resolving them, and the man who had held the entire effort together for half a century was running out of time. Ed Stone became Voyager's project scientist in 1972. The spacecraft would not launch for another 5 years. He was there for the design reviews, the instrument selections, the political battles over funding, the Jupiter flyby, the Saturn decision, the Uranus surprise, the Neptune triumph, and every boundary crossing that redefined the edge of the solar system. 50 years, he held the position longer than most people hold any single role in their entire professional lives. Under his leadership, a mission designed to last 4 years at 2 planets was transformed into the longest-running space exploration in human history. The budget fights alone would have broken most scientists. The grand tour's cancellation, the piecemeal extensions, the constant need to justify the mission's continued existence to Congress, to NASA management, to an ever-changing roster of administrators who did not share Stone's conviction that the outer heliosphere mattered. He navigated all of it, not through charisma or political maneuvering, but through an unshakable commitment to the data. When the termination shock defied predictions, Stone organized the analysis. When the heliopause crossing ignited a year-long debate, Stone managed the competing factions. When Leonard Fisk argued the craft had never left, Stone ensured the dissenting view received fair hearing alongside the majority position. Linda Spilker, who succeeded Stone as project scientist in 2022, described the team's culture in a way that reveals how personal the mission had become. "We had our kids around the same time," she said. "We'd take vacations together. This was not a rotating staff of anonymous engineers. It was a family, aging alongside a spacecraft, bound by a shared commitment to a machine that was always one budget vote away from silence." Jamie Rankin became deputy project scientist at the age of 34. She was born after Voyager launched. The generational handoff was real and urgent. The institutional knowledge carried by Stone, by Gurnett, by the engineers who designed the instruments in the early 1970s, existed nowhere else. When Stone retired and when Gurnett died, that knowledge narrowed. Each departure took something irreplaceable. Suzanne Dodd managed the project with a staff of 15 to 20 people. 15 to 20 for the most distant human-made objects in existence. The team was smaller than the staff of a mid-sized restaurant. Every person on it carried responsibilities that would fill multiple positions at a larger mission. Ed Stone died on June 9th, 2024, at the age of 88. At the time of his death, every central question of the mission remained open. The shape of the heliosphere, the nature of the heliopause, the source of the anomalous cosmic rays, the meaning of Pressure Front 2, the magnetic field mystery at the boundary, 50 years of investigation, and the fundamental question, where does the solar system end, was further from a clean answer than it had been when he started. A new paper was about to arrive that would make that question even harder, and it would challenge the very concept of crossing the heliopause, the achievement that defined Stone's legacy. In 2024, a research team led by Turner published a paper that reframed the heliopause in a way that challenged the fundamental narrative of the entire Voyager mission. The heliopause, they argued, based on analysis of both Voyager datasets and complementary measurements from the Interstellar Boundary Explorer, was not a thin wall, it was a thick boundary layer. A transitional zone of indeterminate width where the solar and interstellar environments mixed gradually rather than meeting at a sharp interface. The implications rippled through every conclusion drawn from the two crossings. If the heliopause is thick rather than thin, then the unchanged magnetic field direction suddenly makes sense. A gradual transition would allow our star's magnetic field to persist deep into the boundary layer, evolving slowly rather than flipping abruptly. The stagnation region, that chaotic buffer zone where the solar wind dropped to zero and reversed, could be reinterpreted as the inner edge of a vast transitional layer rather than a separate phenomenon. The 40-fold plasma density jump detected by Gurnett's instrument might mark one threshold within the layer rather than the layer's outer boundary. But the most devastating implication was for the crossing itself. If the heliopause is a thick boundary layer, then what does crossing it actually mean? Is Voyager 1 in interstellar space? Or is it still inside the boundary, somewhere in the thick transitional fog between our star's domain and the true interstellar medium? Bill Kurth, who had worked alongside Gurnett for decades, stated the situation bluntly. Voyager will not be in the pristine interstellar medium until a boundary is crossed, he said, and it is likely 100 or more astronomical units beyond Voyager 1's present location. Nathan Schwadron, an independent researcher studying the heliosphere's outer structure, concurred. Pristine interstellar space, the space that is truly free of our star's influence, may be 100 or more astronomical units farther out. Run those numbers. Voyager 1 is currently at approximately 165 astronomical units. If pristine interstellar space begins at 265 astronomical units or beyond, the spacecraft has covered barely 60% of the distance to the true boundary. The celebration of 2012, the press conference, the headlines, the first human-made object in interstellar space declaration may have been for an exit that has not yet finished happening. The Turner paper did not claim the crossing was meaningless. The plasma transition was real. The cosmic ray shift was real. Something significant happened at 121.6 astronomical units. But the clean binary framing of inside versus outside collapsed under the weight of the data. The heliosphere does not end with a wall. It fades gradually over a distance that may stretch for hundreds of astronomical units. And Voyager, our only instrument in that fade, is losing power. Each Voyager spacecraft launched with 470 watts of electrical power, generated by 3 radioisotope thermoelectric generators. These generators convert the heat of decaying plutonium-238 into electricity. The decay is constant. The plutonium does not care about budget fights or scientific controversies. It decays at a fixed rate, and with it, the electrical output drops by approximately 4 watts every year. In 2025, each spacecraft operates on fewer than 300 watts. Less power than a typical household appliance. Less than what it takes to run 2 incandescent light bulbs. Every watt must be allocated, and the allocations have become agonizing. The team, led by project manager Suzanne Dodd, with her staff of 15 to 20 people, has been making impossible choices. Instruments have been shut off one by one over the years, each shutdown permanently closing a window onto a region of space that no other instrument can observe. The heaters that keep fuel lines from freezing have been reduced, backup systems have been deactivated. Every conceivable non-essential function has been stripped away, leaving only the bare minimum needed to collect data and transmit it home. In 2025, only 3 instruments remain active on each spacecraft. 3 out of the original suite of 11. On February 25, 2025, the cosmic ray subsystem on Voyager 1 was shut off to conserve power. This was one of the instruments that had detected the heliopause crossing in the first place. The very tool that helped confirm the most significant moment in the mission's history was sacrificed so that other instruments could continue operating for a few more years. Every instrument shutdown is permanent. There is no turning things back on. The power will never increase. The plutonium will continue to decay, the output will continue to drop, and by the early 2030s, there will not be enough power to operate any scientific instruments at all. Voyager will continue to move through space, carrying its golden record and its dead instruments. But it will stop sending data. The investigation has a deadline, and that deadline is approaching faster than any replacement mission could arrive. The Oort cloud, the spherical shell of icy bodies that defines the gravitational boundary of the solar system, begins at roughly 2,000 astronomical units. At Voyager's current speed of approximately 38,000 miles per hour, reaching the Oort cloud will take about 300 years. The craft will be silent long before it gets there. But before the power runs out, the spacecraft itself nearly went permanently silent for a different reason. In late 2023, Voyager 1 stopped making sense. The data stream, already a whisper at 160 bits per second from over 15 billion miles away, turned to gibberish. The flight data subsystem, which packages science and engineering data for transmission, began sending garbled, repetitive patterns that contained no usable information. For anyone who has ever dealt with a corrupted hard drive or a malfunctioning computer, the experience is familiar at a household scale. Now imagine the computer is 15 billion miles away. It was built in the early 1970s. It has 3 million times less memory than a modern cell phone. You cannot physically access it. Every command you send takes over 23 hours to arrive, and every response takes over 23 hours to come back. A single round trip of communication takes nearly 2 full days. The cause was eventually traced to a corrupted memory chip in the flight data subsystem. One chip, among the handful still functioning in the spacecraft's ancient computer architecture, had failed. The data that should have been organized, formatted, and transmitted in recognizable packets was instead being scrambled, repeated, or dropped entirely. There was no way to replace the chip, no spare parts, no repair mission, no robot arm to swap components. The engineers at the Jet Propulsion Laboratory had to solve the problem using only the commands they could transmit across 15 billion miles of space and whatever still functional hardware remained aboard the spacecraft. For 5 months, the team worked the problem. The solution they devised was extraordinary. They took the code that had resided on the corrupted chip, broke it into smaller segments, and distributed those segments across other memory locations elsewhere in the spacecraft's computers. This required writing new software, testing it as rigorously as possible without being able to run it locally on identical hardware. The last ground-based test units were decommissioned years ago. Uploading it across a signal path with a 23-hour one-way delay and hoping the 47-year-old computer would execute it correctly. On April 20th, 2024, science data was restored. The spacecraft was functional again. From 15 billion miles away, engineers had performed surgery on a computer older than most of the people working on it, using a signal weaker than a billionth of a watt, with a 2-day communication lag, and they had succeeded. They had barely caught their breath when, 6 months later, the primary transmitter failed. The heliosphere is not an academic curiosity. It is the radiation shield for every living thing in the solar system. Galactic cosmic rays, high-energy particles generated by supernovae, neutron star collisions, and other catastrophic events scattered across the Milky Way permeate interstellar space. They travel at close to the speed of light. They carry enough energy to damage DNA, degrade electronics, and alter the chemistry of planetary atmospheres. Without the heliosphere deflecting and attenuating the majority of these particles, Earth's surface radiation environment would be dramatically different. The measurements at the heliopause confirmed this directly. When Voyager crossed the boundary, galactic cosmic ray counts jumped by a factor of 3. Inside the heliosphere, the bubble absorbs and deflects the majority of incoming galactic radiation. Outside, the full force of the galactic particle environment is unshielded. The heliosphere reduces cosmic ray exposure on Earth by roughly 2/3. Every organism that has ever lived on this planet has done so under the protection of that bubble. But the implications extend beyond the present moment. Our star is currently moving through a region of relatively low-density interstellar gas called the local interstellar cloud. The heliosphere's size and shape reflect, in part, the density of the material pressing against it from outside. A denser medium compresses the bubble, shrinking it, reducing its shielding effectiveness. A less dense medium allows it to expand. Within approximately 2,000 years, our star is projected to enter a region called the G cloud, a denser patch of interstellar material. A denser external medium would compress the heliosphere significantly, potentially shrinking the protective bubble and exposing the inner solar system to higher levels of galactic cosmic radiation. How much higher depends on the heliosphere's shape, thickness, and the dynamics of the compression. the very questions that Voyager's data has shown we cannot yet answer. The shape debate matters. The thickness of the heliopause matters. The stagnation region, the magnetic field anomaly, the unknown structure of the interstellar medium ahead, all of it feeds into a question that has direct consequences for life on Earth. How resilient is this shield, and what happens when it gets squeezed? Understanding that shield depends on instruments that are failing right now aboard a spacecraft that the government may not fund long enough to provide answers. Voyager is not run by an army. The mission that operates the most distant human-made objects in existence employs a team smaller than the staff of most neighborhood restaurants. Suzanne Dodd manages the project. Linda Spilker, who took over as project scientist after Ed Stone's 50-year tenure, carries the scientific direction. Jamie Rankin, the deputy project scientist, was 34 years old when she was appointed, born years after the spacecraft launched. The entire staff numbers between 15 and 20 people. These are not interchangeable positions. The institutional knowledge required to operate Voyager, to understand its ancient computer architecture, to troubleshoot instruments designed half a century ago, to interpret data from a spacecraft whose documentation exists partly in the memories of people who have retired or died, cannot be transferred through training manuals. It lives in the people who have spent years or decades on the mission. Linda Spilker's description of the team captures something that formal org charts cannot. "We had our kids around the same time," she said. "We'd take vacations together." This is a team bonded by shared decades, shared milestones, shared anxiety over budget votes and instrument failures, and the slow, relentless decline of a power source they cannot replenish. Cummings was described as the last person to touch both Voyagers before launch. That phrase carries weight. The physical connection between human hands and spacecraft hardware. The moment when someone tightened the last bolt or checked the last connection before the rocket carried it away forever. That chain of physical contact links the engineers of the 1970s to the spacecraft now 15 billion miles away. When Ed Stone died in 2024, the institutional memory narrowed. When Don Gurnett died in 2022, it narrowed again. Each departure takes something that cannot be replaced, knowledge that was never written down because nobody thought the mission would still be running 4 decades later. In July 2025, the threat became institutional rather than personal. More than 280 NASA employees signed a public declaration protesting proposed budget cuts that would slash NASA's science funding by 47%. Voyager, already operating on minimal staff and minimal power, was among the missions at risk. The Deep Space Network, the system of massive radio dishes in California, Spain, and Australia that receives Voyager's signal, requires funding to operate. Reduced budgets mean fewer hours of listening time. For Voyager, whose signal is already at the threshold of detectability, any reduction in ground station availability could mean losing data that can never be recaptured. Silence on the ground is indistinguishable from death in space. Yet, even as the mission faces threats from both physics and politics, the spacecraft pulled off one more engineering miracle involving hardware that nobody had thought about in 4 decades. In 1977, Anne Dryan sat in a laboratory and had her brainwaves recorded by an electroencephalograph. The electrodes traced the electrical activity of her brain for approximately 1 hour. The resulting data was compressed into roughly a minute of audio and etched into both golden records mounted on the Voyager spacecraft. Days before the recording session, Dryan had fallen in love with Carl Sagan during a late-night phone call about the record project. They had told no one. The relationship was new, secret, and electric. As the electrodes mapped her neural activity, Dryan later said she was thinking about the history of Earth, about love in the abstract, and about what it felt like to fall in love with a specific person in a specific moment. Knowing that these electrical patterns would be pressed into a gold-plated copper disc and flung beyond the reach of our star, Sagan later divorced his wife, Linda Saltzman Sagan, who had also worked on the Voyager project. The personal cost was real and messy, a professional collaboration fractured by a love affair that began over a phone conversation about what sounds to send to the stars. There is nothing tidy about it. There is nothing symbolic or metaphorical. It is simply a thing that happened, entangled with the creation of an artifact that now travels through whatever region of space Voyager occupies. Those brainwaves are currently approximately 15.4 billion miles from the lab where they were recorded. They are traveling at 38,000 miles per hour through the thick boundary layer of the heliopause, or perhaps through the interstellar medium, or perhaps through something in between that science has not yet found a name for. A recording of falling in love, encoded in the universal language of electrical oscillations, carried by a machine whose own survival has become an improbable love story between a tiny team of humans and a dying spacecraft. The golden record was designed as a message from our species to anyone who might find it. In practice, the odds of another intelligence encountering either Voyager spacecraft are so vanishingly small that the record functions differently from its intent. It is a message from us to ourselves, a declaration of what we thought was worth preserving at a particular moment in our history. Music, images, greetings, sounds, and the brainwaves of a woman secretly falling in love. Everything about Voyager is human like this. The budget fights, the naming confusion, the dead instrument, the arguments about whether the craft actually left, the team that raised their children alongside a spacecraft, the love affair that burned through a marriage and left its neural trace sailing past the heliosphere. And in October 2024, the most human thing of all happened. The spacecraft nearly died, and something built 4 decades ago, unused and nearly forgotten, woke up to save it. In October 2024, Voyager 1's primary X-band transmitter failed. The X-band system had been the main communications link between the spacecraft and Earth since launch. It operated at a higher frequency and data rate than the backup, providing the signal that the Deep Space Network had been tracking for 47 years. When it failed, the connection between Earth and its most distant explorer went dark. For a spacecraft 15 billion miles away, losing the primary transmitter should be a death sentence. There is no service call, there is no replacement part. There is no second chance when your equipment is farther from the nearest human than any object has ever been. But Voyager 1 carried a backup, an S-band transmitter, installed alongside the primary system before launch, designed as a failsafe for exactly this scenario. There was one detail that made its survival unlikely. The S-band transmitter had last been used in 1981, 43 years of dormancy. 43 years floating through the vacuum of space, subjected to cosmic radiation, temperature extremes, and the cumulative degradation that time inflicts on all electronic components. Nobody knew whether it would work. The spacecraft's onboard fault protection software detected the X-band failure. Without any command from Earth, without any human intervention, the software executed a pre-programmed response. Switch to the backup transmitter. The command traveled through circuits that had been carrying current for 47 years, reached a transmitter that had been silent for 43 of those years, and asked it to power up. It activated. A transmitter built in the early 1970s, last used when the first space shuttle had not yet flown, powered up and began sending data home. The signal was weaker. S-band operates at a lower frequency and supports a lower data rate than X-band, but the signal was there. The Deep Space Network detected it. Engineers on the ground, most of whom were not born when the backup was last active, confirmed the signal and began processing data. The mission was alive. 43-year-old hardware, designed by engineers who had long since retired or died, manufactured by companies that might no longer exist, built to specifications that predated the personal computer, had saved the most distant human-made object from permanent silence. No simulation had tested this scenario. No ground-based prototype existed to validate whether the backup would function after 4 decades of disuse. Engineering textbooks teach redundancy as a design principle. What they cannot teach is the strange alchemy of a backup system that works after 43 years for reasons that engineering models cannot fully predict. Some combination of quality manufacturing, conservative design margins, and pure luck kept those circuits viable across 4 decades of cosmic radiation and vacuum exposure. The probe communicates on that backup system now. Every bit of data from interstellar space, every cosmic ray count, every magnetic field measurement arrives on Earth through a transmitter that was last active when the Cold War was at its height. In July 2025, 280 NASA employees added their names to a public declaration. The document protested proposed budget cuts that would reduce NASA's science funding by 47%. Voyager was listed among the missions at risk. The arithmetic of the threat was simple. Voyager requires the Deep Space Network to receive its signal 3 stations around the world, in California, Spain, and Australia, maintain massive radio dishes capable of detecting the craft's impossibly faint transmissions. Those stations serve multiple missions. Reduced funding means reduced operating hours. Reduced operating hours means some missions lose antenna time. For a spacecraft whose signal arrives at the strength of 10 to the minus 16 watts, every hour of lost antenna time is an hour of lost data from a region of space that no other instrument can reach. All 280 signatories were making an argument that transcended any single mission. Both Voyager spacecraft are irreplaceable. There is no backup mission. There is no spacecraft under construction that will reach interstellar space in our lifetimes. The distance the probes have covered took nearly 50 years of continuous flight. Any replacement launched today, using current propulsion technology, would take decades to reach the heliosphere's boundaries and would arrive after the original Voyagers had long gone silent. Every measurement Voyager is collecting right now about the thick boundary layer of the heliopause, about pressure front 2, about the magnetic field anomaly, about the structures in the interstellar medium, cannot be collected any other way. If funding cuts silence the ground stations before the power runs out, the data will be lost. The spacecraft will continue to transmit faithfully on its 43-year-old backup transmitter, and nobody will be listening. None of this is hypothetical. The cuts were proposed. The declaration was signed. The political process that will determine Voyager's fate is ongoing. The same type of congressional budget decision that nearly killed the mission before it launched 50 years ago, when the Grand Tour was deemed too expensive, now threatens to end it before the investigation is complete, and the investigation is nowhere close to complete. The shape of the heliosphere is unknown. The thickness of the heliopause is unknown. The source of the anomalous cosmic rays is unknown. Pressure front 2 is unexplained. The magnetic field anomaly at the boundary is unresolved. The question that launched this entire endeavor, where the solar system ends, remains genuinely open. What lies ahead for the spacecraft that may or may not survive long enough to continue asking reveals just how little of the frontier has actually been explored. Voyager 1 is currently approximately 165 astronomical units from our star, traveling at roughly 38,000 miles per hour. That speed sounds enormous. In the context of interstellar distances, it is barely a crawl. The Oort cloud, the vast, spherical shell of icy bodies that marks the gravitational boundary of the solar system, begins at roughly 2,000 astronomical units. At current speed, Voyager 1 will reach the inner edge of the Oort cloud in approximately 300 years. It will not pass through the cloud for roughly 30,000 years. The Oort cloud is so enormous that even at 38,000 miles per hour, traversing it takes longer than the entirety of recorded human civilization. In approximately the year 40,272 of the Common Era, Voyager 1 will pass within roughly 1.6 light-years of a dim red dwarf star designated Gliese 445 in the constellation Camelopardalis. By then, the spacecraft will have been dead for tens of thousands of years. a silent artifact carrying a gold-plated copper record and the residual charge of instruments that ran out of plutonium in the 2030s, drifting through the neighborhood of another star. Consider what these numbers mean for the central question. If the boundary of the solar system is defined gravitationally, by the extent of our star's gravitational influence over comets and icy bodies in the Oort cloud, then Voyager has not even covered 1/10 of the distance to the edge, 165 astronomical units out of 2,000. A fraction. The gravitational solar system is vastly larger than the heliosphere, and Voyager is nowhere close to its outer boundary. If the boundary is defined by the heliopause, the plasma transition that both spacecraft detected, then yes, Voyager crossed in 2012. But Turner's thick boundary layer means the craft may still be wading through a transitional zone, not yet in pristine interstellar space. Bill Kurth's estimate puts the true interstellar medium 100 or more astronomical units farther out. At that distance, the answer to "Has Voyager left?" becomes maybe, partially. It depends on how you define left. If the boundary is defined by the pristine interstellar medium, uncontaminated by any trace of our star's influence, then Nathan Schwadron's estimates suggest the craft has potentially hundreds of astronomical units still to go. The answer, by this definition, is clearly no. The question of where the solar system ends does not have one answer. It has multiple answers, each corresponding to a different physical definition, and Voyager's data has made every definition more complicated and less satisfying than it was before we had measurements. In 2012, the world was told that Voyager 1 had left the solar system. The data tells a different story, not a simpler story, not a cleaner story, a stranger, more unsettled story that remains incomplete. The termination shock was not symmetric. The heliosphere is lopsided, pressed inward on one side by the interstellar medium. The anomalous cosmic rays were not accelerated, where 50 years of theory said they would be. The pickup ions carried energy that invalidated the energy budget of the termination shock. The plasma detector that could have settled the heliopause debate was dead, broken at Saturn 32 years before the boundary was reached. The stagnation region, a 900 million mile wide zone of chaotic reversed solar wind, appeared without warning in a region no model predicted. The heliopause crossing, when it came, produced the expected particle signatures and the completely unexpected magnetic result. The field direction held steady. 2 crossings, 2 spacecraft, same anomaly. Don Gannett predicted the distance to the heliopause in 1992 and was laughed at. He was right. His instrument settled the debate. He died before the next set of mysteries emerged. Mayor of Ophir modeled the heliosphere as a croissant and was mocked at every conference. Her simulations are now among the leading candidates for the true shape. No consensus exists. Leonard Fisk argued the craft never left. The thick boundary layer, described by Turner, suggests he may have been closer to the truth than anyone acknowledged. The interstellar boundary explorer found a ribbon across the sky that no theory predicted. Pressure Front 2, a persistent wall of elevated density and magnetic pressure in the interstellar medium, has no explanation 5 years after its detection. The heliopause is hotter than the surface of our star. The heliosphere's shape is unknown. Interstellar space has structures that nobody mapped because nobody had an instrument out there to map them. Voyager 1 communicates through a backup transmitter that was last used in 1981. Its primary transmitter is dead. Its cosmic ray detector was shut off in February 2025. 3 instruments remain. Power drops by 4 watts every year, and the plutonium does not negotiate. The team is 15 to 20 people. The budget faces a 47% cut. 280 NASA employees have signed a declaration protesting the decision. The question that launched this investigation, where does the solar system end, is further from resolution today than it was when Voyager launched in 1977. Every boundary the craft crossed turned out to be more complex than predicted. Every model it tested was wrong in ways that generated new questions rather than answers. The edge of the solar system may be a line, or a fog, or a thick transitional zone hundreds of astronomical units wide. It may be defined by plasma, or gravity, or magnetic fields, or the pristine interstellar medium that no instrument has yet reached. And the only machine capable of continuing the investigation is 15.4 billion miles away, powered by decaying plutonium, running on 3 instruments and a 43-year-old backup transmitter, carrying a golden record that holds the brainwaves of a woman falling in love. The investigation is open, the machine is dying, and there is nothing to replace it.